Chapter 3.3, Zeros of Polynomial Functions. Alright, so let's learn the definition of zeros. Okay, let's say p of x. P is a polynomial function, and then if you let p of x equal to 0. So the polynomial is 0, that means all the x values that makes the polynomial, the function 0, is called 0 of p. 0 of the function p. It looks like this. Let's say here is a graph, x-axis, y-axis. And then here is a graph of, this is a polynomial function. Then, okay, p of 0 is, p of x equals 0 means they are the x-intercept, right? X-intercepts. So as you see this, let's say this is like 1, 2, or 1, or, just an example. 5 and negative 4, something like this. Then these numbers, negative 4, 1, 5, are called the zeros of the polynomial. And also it's called roots of the equation, polynomial. Polynomial is an equation, right? Because it is equal to 0. So we call these numbers zeros or roots, or even they are the x-intercepts when the graph crosses the x-axis. So there are different names, but actually they are the same. All right, then if polynomial, so in that case, then we can write the polynomial because we know the roots and the x-intercepts and the zeros. We can write it something like this: x plus 4, x minus 1, x minus 5. Because when we make the polynomial equal to 0, then x values are negative 4, 1, and 5. So each one of this, using each x-intercept, we can write as a factor, product of these factors. So if p of x has x minus a binomial, this is a binomial, as a factor exactly k times, that means, this means p of x can be something like this, x minus 3, like fifth power, x minus 2 to the third power, like this. So occurs exactly 5 times, or in this case 3 times. Then r is a 0 of multiplicity of k. So k is the number of times the factor, this factor occurs. Can you see it? So in that case, the zeros are 3, right? 3, and 3 is a 0 of multiplicity what? Multiplicity of 5. Okay, multiplicity is what? 5. And the 0, and the 0, 2, 2 is another 0, and the multiplicity is what? 3, right? Multiplicity is 3. Okay, can you see it? All right, for example, here's another example. P of x equals x minus 5 squared, and x plus 3 cubed, and x plus 4 only, right? Only means it occurs once. So p of x, the polynomial, has 5 as a 0. 5 as a 0 of what's the multiplicity? Is the power 2. And negative 3 is a 0 of multiplicity what? 3. And negative 4 is 0 of a multiplicity of what? 1, right? 1. All right. Okay, and the next definition is the number of zeros. Okay, then how many zeros are possible? If you set p of x equal to 0, so that means once you set p of x equals 0, then how many intercepts are there? X-intercepts. And how many, same meaning, how many zeros, which means how many x-intercepts? Okay, it's really simple. If the degree of the polynomial is n, okay, something like this. For example, let's say p of x equals, an leading coefficient x to the nth power plus some other functions. All right, then the largest power is n, right? N. So we call it the degree of the polynomial. So the degree of the polynomial is n. Then there are at most the maximum n zeros. So there are n x-intercepts at most. At most. So it may be in a less than or equal to n. It may be less than n zeros, but the maximum is n. All right. And then also this includes the multiplicity k as well. So just keep in mind that the real zeros is maximum at most n. There are n x-intercepts. If there are the complex solutions, then we will decrease the number of n zeros by 2. So at most, okay, this is important, at most n zeros. All right, and then next one is really important and very useful theorem, that is rational zero theorem. Rational zero theorem means, okay, rational means a fraction, right? Fraction. So we want to find, okay, if there is the rational zeros, the x-intercept, okay, x-intercept or the root is a rational number, is a fraction, then the fraction comes from this p over q. All right, so if a polynomial, so we have a polynomial starting with an is the leading coefficient and x to the nth power all the way up to some constant a0. Okay, then this polynomial has, let's say this one has an integer coefficient, and let's say it has the rational zero as a root of the function. So p over q is let's say p over q, I don't know what the p over q is, but let's say p over q is a rational zero, it's a root of the function. Okay, then we say the p, okay, p is a factor of the constant term, a0 is the constant term, right? And then q, the denominator q is a factor of the leading coefficient. What's the leading coefficient? An. Can you see it? All right, so if there is a rational zero, if the root is written in a rational number fraction, then the numerator comes from a factor of the constant, and the denominator q is from the leading coefficient. Okay, let's see an example. Okay, use the rational zero theorem to list all possible rational zeros. So if there is a rational root, then the rational root will be p over q. All right, p over q. Then p is what? Okay, p is a factor of the constant, the last one. Okay, p, what is p? Okay, p is a small letter, lowercase. P's are the factors, okay? Factors of the constant term. All right, so 12 is the constant, right? This is the constant. All right, so p can be, so in that case, we can write p as, what are the factors of 12? It can be 1, 2, 3, 4, 6, and 12. These are the factors of 12. How about q? Okay, q is the factors of what? The leading coefficient, right? Leading coefficient, which is a0, I'm sorry, an. Then they are what? It is 4, right? It is 4. So the factors are 1, 2, and 4. All right. So let's write p over q. P over Q are, okay, we can, negative number is also possible. So we will just use plus or minus. Okay, plus or minus, sorry. So plus or minus, plus or minus. Okay, even this one. All right, so you can write it plus or minus 1. Let me just combine everything. So plus minus 2, plus minus 3, plus minus 4, 6, 12. Then the denominator is this one. Then we're going to write all possible rational zeros, right? So using 1 and 1, that is 1, right? Plus or minus 1. And then we're going to use all of them, right? So like this. So combine one number from the denominator, combine another number in the numerator, then it will be, there are so many things, right? So many. So even if we try like this, then it will be plus or minus 1 over 2. And then plus or minus 2. Even there's plus minus 1 over 4, right? 1 over 4 like this. So many possible. So let's try one by one. And then also 2 over 1 is 2. 2 over 2 is 1, right? 2 over 2 is 1, so that is already included here. And 2 over 3, so we plus or minus 2 over 3. Plus or minus 3 over 4. And then 4, we're using this one. 4 over 1 is 1. 4 over 1 is 4. And then 4 over 2. Plus or minus 4 over 2. That is what? Isn't it same as 2, right? Same as 2. Okay, and then 4 over 4. Okay, 4 over 4 is same as 1. And then let's use 6 and 1. So plus or minus 6. And then 6 and 2. So 6 over 2 is 3. I think I skipped 3, right? I skipped 3. Okay, let's try plus or minus 3. Okay, plus or minus 3. There's so many. So 3 over 2. So plus or minus 3 over 2. And then 3 over 4. Plus or minus 3 over 4. And then 4, right? We got 4. And the 4 over 2, we already did. 4 over 4 is 1, already did. And then 6 over 1 here. And 6 over 2 is 3. It's already here. And then 6 over 4 is 3 over 2. It's already here. And then the last one, 12. So plus or minus 12. And then plus 12 over 2 is 6, already here. And then the next one, 12 over 4 is 3, is already here. So these are all possible rational zeros. Just the possible ones, right? Good. So if this polynomial has a rational root, rational zeros, then it will be one of these. Okay, one of this. All right. Next definition is a little bit confused because we can estimate the upper bound and the lower bound of the real zeros. So this is how how the theorem works. Let's say, okay, this time we will use synthetic division. So let's say p of x is a polynomial function. So an x to the nth power plus an minus 1 x to the n minus 1 plus keep going. And then let's say a0 is a constant. All right, so in this case, okay, let's divide this polynomial by x minus b. Okay, x minus b. So b, we don't know what b is. B will be the upper bound or lower bound depending on the conditions here. So let's start with b equals 1, 2, 3, and so on. And then b is a negative number. So negative 1, negative 2, negative 3, and so on. So we're going to divide the polynomial by positive integers and negative integers. So once we divide it, the polynomial by x minus b, we know how to use synthetic division, right? All right, so let's say b is a positive integer, positive number. And then the leading coefficient, so in this case an, right? An. The leading coefficient is an. This should be an, right? An. So that indicates, so that means A is the positive number, right? And let's say B is also positive number. Okay, then when we do a synthetic division using B, then the bottom here, synthetic division, there are some numbers, blah, 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 right? Let's say positive number 1. And then we got some numbers like, 1, 5, 6, just an example, 3 like this. So these are all positive, right? The last row is all positive, all positive, or 0. So we can, maybe we may have a 0, right? We never know. So 0. So if the last row of the synthetic division, this guy, is composed of positive numbers or zeros, then B is an upper bound. Okay, B is an upper bound, right? So if you start from 1, then if you got this, then 1 is an upper bound. Get it? All right. And then let's say, now the leading coefficient, this time, this one indicates that the leading coefficient is now negative, right? Negative. Of course, the B value, we are dividing the polynomial by a positive integer. Then, if the last line, the bottom row of the synthetic division contains this time negative numbers. So divide this one by, I'm going to divide by, let's say, negative 2. And then we have like a negative 1, 0, negative 2, negative 4, something like this. So if this line contains negative numbers or zeros, then negative 2, this guy is what? It's an upper bound. Okay? It's an upper bound. All right, so this is how we find upper bound. So upper bound is really simple. The last row, so leading coefficient is positive, and we are dividing by a positive number. And then the last row is all positive or zeros. Then that's the upper bound. 1 is the upper bound. And then if you are dividing by a negative number, and then the last row of the synthetic division is all negatives or zeros. Some are composed of negative numbers and zeros, then negative 2 is the upper bound. All right. And then how about the lower bound? Okay, lower bound is, let's say B is a negative number. Okay, so we are dividing the polynomial by a negative number. And then the last row, okay, the last row is, let's say it is like a 1, negative 2, 0, and then negative 3, something like this. Then as you see this, the sign alternates, right? This is positive, this is negative, and 0 can be either positive or negative. So we can use either positive or negative to make the sign alternate. So in order to alternate, let's make this one positive. Then the negative 3 is a negative number, right? And the 5 is a positive number. So the sign alternates, right? The sign alternates. So alternating means one is positive, one is negative. All right, then B is the lower bound. Lower bound of the real zeros of this polynomial. So to find the lower bound, the lower bound in this comes from the negative number. Okay, so if B is negative and the last row of the synthetic division alternates the sign, then this is the lower bound. Negative 2 is the lower bound. All right, so upper bound, B is positive, then everything is positive or 0. If B is negative, if the leading coefficient is negative, then, wait a second. Okay, I made a mistake on this one. So when the leading coefficient is negative and the b is still positive. Okay, b is still positive, positive. All right, so when b value is positive and depending on the leading coefficients, if the leading coefficient is negative, then make sure the last row is all negative or 0. Then 2 is the upper bound. All right, and then if the leading coefficient is positive, then the last row is all positive or zeros. Then 1 is this b is the upper bound. All right, and then if b is less than 0, okay, b is less than 0, so negative number, and the last row is alternates in sign, then what? Negative 2 is a lower bound. Okay. All right, next example. Okay, what is the smallest positive integer that is an upper bound? So we want to find upper bound that is the smallest positive integer. So we will start from positive number 1, 2, 3, and so on until we have all positive values in the last line of the synthetic division. Okay, to find the largest negative integer, then we will use the negative integers to divide the polynomial so that the last row contains alternating signs. Then there will be the lower bound, right? So let's start with positive 1. So write down the coefficients 2, 7, negative 4, negative 14. And let's use positive, start with positive 1 because we want to find the largest, the smallest positive integer that is an upper bound. Alright, so bring 2 down, and 1 times 2, that is 9. 1 times 9 is 9, and then add these two numbers, that is 5. Then multiply, so 5, and add it, so negative 9, right? Look at this, we have a negative 9. We're supposed to have all positive numbers, then 1 will be the upper bound, right? So in this case, there's a negative 9, so 1 is not an upper bound. So let's try 2. Okay, 2, 7, negative 4, and negative 14. All right, 2, then 2 down, 2 times 2 is 4, 11, and then multiply by 2 is 22, add it, 18, 36, and then 12. Look at this. These are all what? They are what? Positive or positive, non-negative. So I would say non-negative because it's a positive or 0, or positive or 0. So non-negative, right? Non-negative. Right, non-negative. So we know that 2 is an upper bound. Right? 2 is the smallest upper bound. Can you see it? Therefore, 2 is the smallest upper bound. All right. Then let's find the largest negative integer that is a lower bound. Okay, then we're going to divide this polynomial by a negative number starting from negative 1. Okay, so if the last row contains alternating signs, then it will be the lower bound, right? I mean the largest negative integer lower bound. Alright, then bring it down, bring 2 down, multiply, add it, multiply, add, multiply, add. So as you see this, the sign does not alternate, so negative 1 is not a lower bound. Then let's try negative 2. Okay, negative 2, then bring 2 down, negative 4, 3, negative 6, negative 10, and positive 26. Even this negative 2 does not make the last row alternating the sign, right? So let's try negative 3. Okay, 2, 7, negative 4, negative 14. Let's divide this by negative 3. Okay, 2 down, so negative 6, 1, negative 3, negative 7, 21, and 7. Okay, this one also, 2, 1, negative 7 and 7. The numbers does not alternate. So let's try one more. 2, 7, negative 4, negative 14. Okay, let's divide this by negative 4. Then 2 down, so negative 8. Negative 1, look at this, 2 and negative 1, sign now alternates. Okay, multiply, which is 4. Then 0, because 0 can be positive or negative. It depends on then alternating the sign. The multiply, 0, add it, so negative 14. Look at this. Okay, this is plus, right? This is positive, negative. So let's make 0 as a positive because we want alternating signs, right? And that is negative. The sign now finally alternates. The sign alternates, right? So what's our conclusion? Therefore, negative 4 is the lower bound, right? Is the largest negative integer lower bound. Is the largest integer lower bound. All right, then if you use a calculator, then the graph looks like this. Okay, using a calculator, here is x-axis, and then it looks like this. Something like this, and this is the y-axis. Y-axis. So this point is around between 2 and 3. Between 2 and 3. Okay, and then this point is between 1 and 2. This is between this 1 and 2, 3, and 4. Negative 4. Right? All right, so as you see this, 2 is an upper bound, right? 2 is an upper bound. The smallest positive integer upper bound is 2. And then it's a negative 4, lower bound. Okay, sorry, so something was wrong. Something was wrong. This should be 1 and 2. Okay, I graphed incorrectly, so this is 1 and 2. So as you see this, the graph is not drawn in scale. So as you see this one, this is the, I don't know what this point, but this one is less than 2, right? Less than 2. So the upper bound is 2, and the lower bound is negative 4, right? Can you see it? All right, so, this theorem works. I re-sketched the graph, and so this makes more sense. So the graph, the x-intercepts are within the upper bound 2 and the lower bound negative 4. All right, next definition is really useful as well. Okay, Descartes' rule of signs. Descartes. Okay, let's say P of x is a polynomial written in descending order by the degrees. So the largest degree comes first. All right, then the number of positive real zeros. Okay, so when we make this P of x equals 0, then what are these x values, right? So what's the number of positive real zeros? Okay, that is equal to the number of variations in sign of P of x, or subtract, decrease it by 2, 4, 6. Okay, this means, let's say, here's an example. Let's say P of x equals 3x to the 4th power minus 5x to the 3rd power. Just an example to help you understand this. All right, look at this. And this polynomial is written in descending order by the degrees, right? And then we will check how many times the sign changes. Now, the variation in sign means, okay, the first one is this is plus, right? This is positive. Okay, so this is positive 3, right? Positive 3. So positive to the negative. So there was one variation. And then negative to negative, that's the same number, right? So same positive, same sign. So there's no change in the sign. But starting from here to here, there is a sign changes. And then plus to minus, also there's a sign change, right? So there were 3 variations in changing signs. So the positive real zeros could be 3. So there may be 3 positive real zeros or decreased by 2. So 3 or 2 positive real zeros. Can you see it? Alright, so we may say in this case P of x has 3, or 3 minus 2 is 1. 1 positive real zeros. Can you see it? May have, right? May have. All right, then how about the negative real zeros? To find out the negative real zeros, we just plug in negative x. So let's rewrite P of x again. So P of x is 3x to the 4th power minus 5x cubed minus 7x squared plus x minus 7, right? So in here, we're going to plug in negative x. Okay, negative x, and then we will find out how many variations are there, changing in sign. So okay, let's plug in negative x to the 4th power, negative x cubed, negative x squared, negative x minus 7. So rewrite it. Then this, x to the 4th power is, is the sign unchanged. And then the next one, the x cubed, so it will be a negative, right? Negative. So negative times negative is positive. It became positive 5x cubed, then negative 7x squared, then negative x minus 7, right? So from here, so we just rewrote the polynomial by substituting the negative x. And then let's count the number of the variations, the sign, how many sign changes. All right, so this is positive, right? Positive to positive. There's no change in sign. From here to here, plus became minus, right? Negative. So there's sign change. And negative to negative, negative to negative, there's nothing. So in this case, P of x may have, P of x has how many? It has one variation sign, right? So it may have one negative real zero, right? Negative real zero. And then 1 minus 2 is a negative, so we can go all the way up to only this one. Can you see it? So there is one sign change, or one sign change. So it may have one negative real zero. All right, so using the Descartes' rule of sign, let's determine how many possible negative zeros and positive zeros. So first, let's find out the positive zeros. Okay, let's find out the variation in sign. So this one, there's 1. So negative to plus, another one. And plus is we don't count it. And the plus to minus, so another one. So there are 3 variations, right? So there are 3 variations in sign. So what? Therefore, P of x has 3 or 1 possible positive zeros, right? Possible positive real zeros. All right. Okay, let's find out This time negative. Okay, negative real zeros. Okay, we need double S. All right, then we gotta put the negative sign, okay, negative x. Replace x with the negative x, and then rewrite the equation. So once we put a negative sign, then always the negative x, the odd x, the odd degree term will change the sign, right? So the even degree stays the same. Odd degree change the sign. X cubed, and the x squared stays the same, and then an x term is an odd degree, so change the sign like this, and then count the number of variations that changes sign. So plus plus plus, and the plus to minus is 1, right? That's it. So there's only one variation. There's a one variation in sign, right? So P of x has one possible negative real zero, right? One real zeros. One negative real zero. All right, then let's try letter B. So we will do the same thing. Let me write it here. So that is P of x equals 2x to the 5th power plus 3x cubed plus 5x squared plus 8x plus 7. As you see this, there is no sign changes, right? Everything, all of them is positive. So there is no variation, or no variation in change, in sign, changing sign. No variation in sign, right? So P of x has no positive real zero, right? All right. How about substituting negative x? So when we substitute negative x, okay, only the positive degree will change the sign. So it will be negative 2x to the 5th power, then negative 3x cubed plus 5x squared minus 8x plus 7. Can you see it? All right. If you're not sure, then let me write it again. So we're going to replace x with what? Negative x to the 5th power plus 3 times x negative x cubed plus 5 times negative x squared plus 8 times negative x plus 7. Then once we simplify this, it's going to be looks like this. So from here, let's count the number of variations in sign. So negative, negative. So negative to positive, here's 1. Positive to negative, another 1. And then negative to positive, another 1. So there are 3 variations, right? 3 variations in sign. So P of x has how many negative? So 3, or decrease these 3 by 2. So there will be 1 negative zeros, real zeros. Okay, can you see it? All right, so these rules are useful when we find out the real zeros. All right, then there's just a guidelines for finding the zeros of polynomial. Of course, this polynomial should have integer coefficients. So we can separate into 3 parts. So the first one is gather general information. That means if the degree of the polynomial is n, then there are at most n real zeros. At most n, right? At n. So keep in mind that one. And also apply the Descartes rule of signs. So we can estimate how many possible numbers of positive zeros are there, and what will be the possible number of negative zeros. So we can just estimate it. Okay, that's how we, gather the general information. And then once we get it, we may use the rational zero theorem, because this rational zero theorem is very useful, because as we mentioned earlier, if the zeros are fractions, then it will be one of the rational zeros. Okay, P over Q. Remember P over Q? All right. So we will, make a list of possible rational zeros. All right, then from there, if we know the upper bound and the lower bound, then we can eliminate all the possible zeros from the list. So we can use only the numbers within this boundary, between greater than the lower bound and less than the upper bound, if we know the upper bound. So in order to get the upper bound and lower bound, we have to start from positive 1, 2, 3, 4, and so on, and then negative 1, negative 2, negative 3, and so on. So we may use upper bound or lower bound. All right. And so important thing is what? Write a list of possible rational zeros. Okay, and then number 3 is work with reduced form. So once we found the zero, then using the system of using the synthetic division, then the last row is a reduced polynomial, right? So from the reduced polynomial, we repeat this process. So do the number 1 and number 2 until we have a polynomial with degree 2. So once the polynomial degree 2, that is a quadratic formula, right? Quadratic form. So we can use a quadratic formula or factoring method to find the two solutions. Can you see it? All right. Let's try example. So we have a polynomial. We want to find the zeros of this polynomial. So let's gather some information. What is the degree? Degree of the polynomial is 4, right? So this implies that there are 4 real zeros at most. 4 real zeros at most, right? At most. So we may have 4, 2, or 0. Okay, 0. Okay, and then let's find out. Okay, let's use the Descartes rule for the number of positive real zeros and to find the number of negative real zeros. Okay, so what is the sign change? So P of x, okay, P of x equals, okay, let me save time. So let's see the sign changes. So, they are all positive, isn't it? The coefficients are all positive, right? Positive. All positive. Positive signs, right? Signs. This means there is no sign changes, right? No sign changes. No variation in sign. No variation in sign. Right? That means there is there's no positive real zeros. That means no positive real zeros. Okay, so there's no positive zeros. How about P of negative x? So let's try P of negative x, and let's find out how many variations in sign are there. All right, so plug in negative x for x, then the P of x will be, okay, the degree is 4, so don't change the sign. We don't have to change the sign. And then x cubed. X cubed will be negative 23x cubed. And then plus 56x squared. And x term becomes negative. Change the sign. All right, then let's find out the variations in sign. So here is sign changes. Here's another one. Here is another one. Negative to positive is another one. So there are how many? There are 4 variations in sign changes, right? So there are 4, subtract 2 from here, also 0. So there are 2, 4, or 0 negative real solutions, real zeros. Can you see it? So there are 4, 2, or 0 negative real zeros. Okay, so the number of negative real zeros may be 4, 2, or none. All right, so let's try from here. So then number 2 is what? Check the suspects. So that is, we will use P over Q, right? P over Q. Okay, we know that there is no positive, there's no positive real zeros. So we will ignore the positive numbers. We will deal with only the negative numbers. Okay, negative numbers. So this is the P. What is P? P will be the factors of 16, right? And Q will be the factors of the leading coefficient Q. So P is what? Plus or minus 1. So we don't need positive. So we will just use a negative, right? Negative numbers. Just negative numbers. So negative 1, negative 2, negative 4, right? Negative. And negative 8, negative 16 over. Okay, the factors of 3 is 1 and 3, right? 1 and 3. The result has to be negative. So the combination of this is there are so many. So negative 1, negative 2, negative 4, negative 8, negative 16, and negative 1 over 3, negative 2 over 3, negative 4 over 3, negative 8 over 3, finally negative 16 over 3. So these are possible real zeros, real zeros. Okay. All right, then okay, from this one, let's get the upper bound and lower bound. In order to find the upper and lower bound, we need to start from 1 to 3, and negative 1, negative 2, and negative 3. So while you are finding the lower bound or upper bound, if the remainder is 0, then we found what? The real 0. So let's start from negative 1. Okay, so I want to divide the polynomial by negative 1. So let's use the synthetic division this time. All right, so write down the coefficients: 3, 23, 56, 52, 16, and divide this by negative 1. Okay, then 3 down and multiply these two numbers, negative 3, add it, multiply, add it, multiply, add it, multiply, and 0. Look at this. Since we have a 0 as a remainder, then negative 1 is a solution. So in this case, we can rewrite the polynomial. So the polynomial, the one of the factor is x plus 1, right? Because we know that x equals negative 1. So negative 1 is a solution. It's a 0 of the function. So that means we can rewrite it. And then this will be a product of x plus 1 and what? The remainder, which is, this is, okay, the last one is x term. The constant x. This constant, this is x, this is x squared, this is x cubed, right? So we can write it as 3x cubed plus 20x squared plus 36x plus 16. So from this, we can, repeat this step. Gather general information, and then use P over Q to find the possible, real zeros. So, okay, for the Descartes rule, it's always the same. Even we have this one, it's always the same. So we have only negative. There will be a negative real zeros. All right, then how about the P over Q? Okay, P over Q is actually, similar, is same as the previous one. Similar to the previous one, but we can reduce it down because we already found negative 1, right? So let's try what P of Q is. They are all negative numbers, right? Negative numbers. So 1, negative 1, negative 2, negative 4, negative 8, negative 16, right? Over the denominator. So denominator is the factors of the leading coefficient 3. So 1 and 3. So possible things is the integers, those integers. And then the fractions. Negative 1 over 3, negative 2 over 3, negative 4 over 3, negative 8 over 3, and negative 16 over 3. So if there is a real 0, then it will be one of this. So we already used negative 1, but you can still negative 1 again because the multiplicity, you remember multiplicity, the same real 0 can occur many times. Alright, so using this one, okay, let's use this one again. Erase this part. We don't have to erase it. So let's do another synthetic division from here. And then let's check whether, okay, let me try it again separately. So from here, let's try this time. Negative 2. Okay, negative 2. And in this case, we don't have to find the upper and lower bound. As we go, negative 2, negative 3, negative 4. And then if the last row is all negatives or zeros, then it's a lower bound, right? All right, so let's try negative 2. Then bring 3 down, negative 6. Then that is 14. Multiply negative 28. So that is positive 8. Negative 16 is 0. We found another one. So that means x equals what? Negative 2. So we can rewrite the polynomial so that it is product of x plus 1 and x plus 2, right? Because you can move negative 2 the other side. And then the last one is 3x. Is it quadratic? This is the last row is a quadratic, right? Quadratic. So 3x squared plus 14x plus 8, because this is constant. 14 is the coefficient of x. This is x squared, right? All right, then since we have quadratic, we can use quadratic formula or factoring method. So this is x, 3x. And 8 is what? 2 times 4. Okay, 4 times 2, right? Then multiply this, then there is 12x. Multiply this 2, then 2x is 14x. Bingo. So this trinomial is the product of these two terms. So finally we can write x plus 1, x plus 2, x plus 4, and 3x plus 2, right? So the solutions are, in this case, once we make this polynomial to 0, if we make the polynomial equal to 0, then the solutions are what? X equals negative 1, negative 2, negative 4, and negative 2/3, right? 2/3. So these are the solutions. So look at this. The degree is 4, right? Degree is 4. So there are at most 4 real zeros. So there are 4 real zeros. If there is a complex solution, then we will reduce this by 2. Decrease the number of solutions by 2. All right. So we didn't even found the lower bound yet, but while we are finding lower bound, we already found the solutions. All right. So whenever you found a solution, then use the result to find another solution. So we gotta repeat the process again and again. Okay, next example is an application. Actually, K is the level of, when you stack a glasses, there's a level 1, level 2, level 3. So the glasses are on top of the bottom and it's also top of the floor. So let's say T is the number of glasses and K is the level of the glasses in a stand. All right, then if there are 220, we want to use 220 glasses, then how many levels can be stacked? That's the question. All right, then in order to find this, K, well, you just plug in 220, and then we need to make this one 0, right? Let's just use, this is solving an equation. So multiply 6 each side. So that will be 1320 equals k cubed plus 3k squared plus 2k. And now move 1320 to the right side and it becomes negative, right? So k cubed 3k squared plus 2k minus 1320 is equal to 0. Alright, so we want to solve this one. So what are the zeros of these equations? Alright, then Descartes' rule, okay, the sign changes only once, right? The sign changes only once. So there is one positive solution. So k has to be positive, right? So there's only one positive solution. Then let's find k. Then how about the p over q? Remember p over q? There are so many possibilities here. So it will be a factors of 1, 3, 2, 0. There are so many factors of this one. Right, so many. So it can be factors, right? Factors of this. So 1, 2, 3, and so on. So many. All right, so let's start from 1. Well, 1 is not enough. So maybe you can find the upper limit, but in this case, you have to try, right? You have to try. Divide this polynomial by 1, 2, 3 all the way until the last row becomes 0, right? Becomes all positive. So if I cheat it, then 12 is the upper bound. Okay, 12 is the upper bound. So the solution should be less than 12. So why don't we try dividing by 11, 10, 9, and so on. That makes sense, right? So let's divide the polynomial using synthetic division, starting from, let's use 10. Get 10. How did I get 10? I cheated. All right, so 1. So 1 times 10 is 10. Then this is 30, 13, right? Multiply, so 130. Then add it, 132. Look at this. This is 1320, and the sum is 0, right? 0. So we can rewrite it. So that is a k minus 10 times k squared plus 13k plus 132 is equal to 0, right? Anyway, from here we know that k equals 10, right? 10. Do we need to find another case? No need, because we know that there's only one positive real 0, right? We don't need to find out negative case. So the level of this glass stack is what? 10 levels. All right. Okay, let's try next one. Okay, next example is there is a cartridge for the the air gun. So carbon dioxide cartridge looks like this. It's a cylinder, and at the end it's a hemisphere. And the volume is given. The volume is 2 pi cubic inches. And the volume of this cartridge should be the volume of the sum of the volume of the cylinder and the volume of 2 hemispheres. So once you add the hemisphere, then it will be a circle, right? It will be a sphere. So actually the volume will be the sum of the cylinder and the sphere. Okay, spheres. So the volume is given. So rewrite the equation. The volume is 20. And then pi r squared. R is the radius. So in this case, the radius is x. Let's use x. So x squared times h. H is the height of the cylinder, which is 4. And then the sphere, the volume of a sphere is 4/3 times pi r cubed, right? Then pi So r is x, so x cubed. So let's solve this. So from here, let's multiply each side by 3. Then there will be 60 equals 4 pi x squared plus 4 pi x cubed. You know, pi is a number, right? 3.14. Sorry, I copied it incorrectly. This is 2 pi, isn't it? 2 pi, sorry, that's 2 pi. 2 pi, right? 2 pi. So multiply by everything by 3. So let's multiply everything by 3. Then there will be 6 pi equals 3 times 4 is 12, right? 12 pi x squared plus 4 pi x cubed. And then divide each side by 4. 2. Let's divide each side by 2. So divide by 2, 2. So 2 pi. 2 pi. 2 pi. Then we have 3 equals 6x squared plus 2x cubed. So rewrite it. Then 2x cubed plus 6x squared minus 3 is equal to 0. So in that case, actually the zeros are not fractions. The zeros are decimals. So in that case, we cannot actually use it. So in this case, use the graphing calculator. Okay, use a graphing calculator to find the solution. Then x will be approximately 0.64 inches. Okay, this is just use the calculator. So what we did is just write an equation. Okay, write an equation depending on the given information. That's it. And then plug in this equation to the graphing calculator and get the zeros of the function. That's it. So the radius is approximately 0.64 inches. All right, that's it for this section. So this section is useful, to find the zeros of a function. It's complicated, right? There are so many things to memorize, but just keep in mind that there are methods to finding possible zeros.